Hello everyone. This video is on section 2.3, polynomial functions and their graphs. Go ahead and access the notes from my website and follow along. A polynomial is a function of this form. A sub n, which represents a coefficient, times x to the nth power, plus another coefficient times x to the n minus 1 power, plus dot dot dot, plus, and then you have an x cubed, an x squared, an x, and a constant term. We just have to make sure that the exponents on the x are whole numbers. All right, so the degree of a polynomial is the highest exponent on the x. So in this example, the degree is n. The leading term is the term that contains that highest exponent. So we have a sub n times x to the nth power. That's the leading term. The leading coefficient is the coefficient of the leading term. And the constant term is a sub 0, the term that doesn't have any x attached to it. Now, keep in mind that a sub 0 can also be thought of as a sub 0 or a naught times x to the 0 power, because x to the 0 power is 1. And so it actually follows the pattern, and 0 is a whole number. Examples of polynomials. Well, here's some basic ones. X squared plus 3x minus 5. Notice that all the exponents on the x are whole numbers. Sometimes you can have higher degree, like negative 5x to the 4th minus 2x cubed plus x minus 7. Now f of 3x minus 1, that's a polynomial. Linear and quadratic functions are polynomials. In fact, f of x equals to 6 is a polynomial because it can be thought of as 6 times x to the 0 power. All right, the first key feature of a polynomial that we're going to look at is end behavior. End behavior is how a graph behaves on its left and right extremes. It's determined by the degree and the leading coefficient. Now, let me show you some examples up over here. Sometimes polynomials look like that. Sometimes they look like that. Sometimes they look like that. Now let's examine these. On the far right extreme of this first one, the graph goes up. On the far left extreme, the graph goes down. Here, far left and far right both go down. Here, the far left extreme goes up and the far right extreme goes down. Well, looking at the degree and the leading coefficient will help us figure out what the end behavior should be. The far left extreme and the far right extreme. And it has to do with whether the degree is even or odd and whether the leading coefficient is positive or negative. Now I'm going to draw stick figures to represent the end behavior. These stick figures' arms will determine the end behavior. An even degree positive leading coefficient will go up to the right as well as up to the left. Classic example would be y equals x squared. Number 2, an even degree and a negative leading coefficient will be down and down. And so maybe negative 3x squared. It could also be x to the 4th, x to the 6th. So it looks like when the degree is even, the end behavior, the left and right end behavior are the same. All right, what about when it's an odd degree and a positive leading coefficient? Well, it's going to be up to the right, down to the left. Classic example would be y equals x cubed. Positive 1x cubed, positive 1x cubed. Okay? All right, and finally, number 4, odd leading degree and negative leading coefficient means down to the right and up to the left. An example could be negative x to the 3rd plus 2x minus 3 or something like that. Okay? Okay, now The next thing we want to look at in terms of a graph of a polynomial is the multiplicity of each x-intercept. When a polynomial is factored, we will see a bunch of factors, binomials, being multiplied. When you have x minus c to the first, c is an x-intercept. Here, an exponent of 1 means we have a multiplicity of 1. Here we have a multiplicity of 2, here we have a multiplicity of 3, and here we have a multiplicity of 4. A multiplicity of 1 will create an x-intercept where the graph goes through the x-axis pretty cleanly. A multiplicity of 2 will be a bounce off of the x-axis. A multiplicity of 3 will go through, but it's going to flatten before it goes through. So I like to call this the flat cross. And then multiplicity of 4 bounces, but it flattens a little bit more when it bounces. So sometimes I call that a flat bounce. All right, notice that the odd multiplicities, 1 and 3, the graph goes through. So we're going to call that crosses the x-axis. So I'm going to say crosses the x-axis. Okay? And then when you have a multiplicity of that's even, like a 2 and a 4, it bounces. So I'm going to say it bounces off the x-axis. Okay? The higher the degree, the higher the multiplicity, the flatter your graph gets at the x-intercept. So here we have multiplicity and we have end behavior. Now it's time to do some examples of graphing polynomials. All right, here we have a polynomial that's factored. It's in factored form. Now, if we wanted to write it in general form, which was the form that we saw in the first slide, you would just multiply everything out. Now, let's see what would happen if you multiply everything out. This part would be x squared something something something. If you bring in this part, then you'll have, or let me put it this way. If I have this part, x cubed, and I were to multiply this whole thing, I would have x to the 5th, because x to the 3rd times x to the squared is x to the 5th. And then if I bring this part in, which is an x squared, and bring it all in, I would have x to the 7th. So all this is to say that the degree is 7. Now, what would be a fast way to determine that the degree is 7? All you have to do is add all the multiplicities and you would have the degree. So let me make that super clear. When your polynomial is in factored form, you have to add up the multiplicities in order to get the degree. So here we have multiplicity of 2, multiplicity of 3. Here I have a multiplicity of 1, and I have a multiplicity of 1. So 2 plus 3 plus 1 plus 1 equals 7. So the degree here is 7. So I don't have it written here, but it's good to remember that the degree is 7. Okay, now if the degree is 7, and the leading coefficient is -3. So how do I know it's -3? It's just the number in front of everything. Okay? That's the leading coefficient. So this brings us to which dance move, which end behavior. Well, it's an odd degree, so the two ends are going to go in opposite directions, and the leading coefficient is negative. So there's my end behavior. So let me draw it right here. So I'm going to represent my end behavior using my stick figure. You could also represent it just by doing something like that. Okay. Now the x-intercept, you just look at each factor and see what makes them 0. So let's look at this first one right there. X squared. It's like x minus 0 all squared. So the first x-intercept, if I go from left to right on in my formula, is 0. The next one is 3. The next one is negative 2. And the next one is 6. So I went left to right on my formula here. 0, 3, negative 2, and 6. Now the y-intercept is a little bit harder now. I have to make x equal to 0. So if I make x equal to 0, so notice that I am plugging in 0 in for x. Well, this 0 is going to make the whole thing 0. So the y-intercept is 0. Now it's time to graph. All right, so the first step to graphing is to find all your x-intercepts. So I got negative 2, I got 0, I got 3, and I got 6. So I'm going to make these dots over here to represent the x-intercepts. Okay, now I have to know which is a bounce and which is a cross based on the multiplicity. Okay, going from left to right again. For 0, right there, I have an exponent 2, so that's a bounce. For the 3, I have an exponent 3, so that's a cross. For the negative 2, I have an exponent 1, so that's a cross. And for 6, I have an exponent 1, so that's a cross. Okay, so now I just need to keep in mind that I need to bounce off of the 0 and cross the 3, the negative 2, and the 6. Furthermore, the 3 is a flat cross because the multiplicity is 3. I am referring to over here. Okay? All right, now how do I start drawing this graph? Well, I can look at the end behavior and know that the graph needs to come down from here. Okay? Then I bounce off of the 0, have to cross the 3, and I have to cross the 6. And here's my graph. Okay, to reiterate, I need to cross there, bounce there, cross here, and cross here. But I made a mistake. I needed to flat cross at 3, and I didn't quite do that. So I'm going to erase that part, and I want to make sure that I'm flat crossing right there at 3. So notice that I did a little flattening of the curve right where the graph crosses an x-intercept of 3. All right, let's look at the next example. Now this next example, the graph is in general form. It's not in factored form. Now the nice thing about the general form is that immediately we know that the degree is 3. And so we would know that the end behavior, because the leading coefficient is 1, which is positive, and the degree is 3, which is odd, that the end behavior would be up on the right-hand side and down on the left-hand side. Okay, that's the end behavior. However, to get the x-intercept, I'm going to need to factor this. So I'm going to factor by grouping. This one lends itself to factoring by grouping because the coefficient of the first two terms have a 1 to 3 ratio with a negative in the middle. And here we have a negative 4 and 12, which also has a 1 to 3 ratio. So out of the first two terms, I'm going to factor out an x squared, leaving me with x minus 3. From the last two terms, I'm going to factor out a negative 4, which leaves me with x minus 3. They both have an x minus 3, and so I can factor that out from the two terms. So I have x minus 3 and then I have x squared minus 4 remaining. So in the end, my function is going to be x minus 3, x plus 2, x minus 2. So we can easily see that the x-intercepts are 3, -2, and 2. The y-intercept is when you make x equal to 0. So the fastest way to do that is to just look back at this original, plug 0 in for x, you'll just be left with 12. And so the y-intercept is 12. Now it is time to graph. Notice that all these x-intercepts have multiplicity of 1. So they all cross the x-axis. Okay? And there's no flat crosses because the multiplicities are all 1, not 3, not 5. And so we just do a flat cross. I mean, a clean cross, if you will. All right, so I'm going to mark on my graph my 3 x-intercepts. -2, 2, and 3. Now looking at the end behavior, I can see that I can start my graph from the bottom because of how the graph looks. So I'm just going like this. Notice, like we said earlier, all the x-intercepts are clean crosses. And as you can see, my graph matches the end behavior that I'm supposed to have. All right, and then maybe I should also label the x-intercept here, the y-intercept here as 12. Okay, so there it is. Okay. The last thing we're going to look at in this lesson is something called the intermediate value theorem. The word intermediate means between. And so let's see. If f of x is a polynomial, and f of a and f of b have opposite signs, then blank. So before I write down what's in the blank, let's see. Let's say, look at my first graph here. Let's say that my f of a is down here. Notice that f of a is negative because it's below the x-axis. And let's say that my f of b is over here. So here I have an example where f of a is negative and f of b is positive. So indeed, f of a and f of b have opposite signs. One's negative and one's positive. Now, a polynomial is continuous. I have to connect those two graphs. Now, there could be a number of ways we could connect the two graphs. I can connect the two graphs just very simply like this. Or maybe it had more humps, more ups and downs. No matter what though, notice that my graph has to cross the x-axis at least once. Sometimes I can cross it more than once. Sometimes I can cross it just once. Here, the red graph crosses the x-axis 3 times between a and b, whereas the blue graph crosses the x-axis just once. Can I make a polynomial cross the x-axis or touch the x-axis twice between a and b? Yeah, check this out. The green graph touches the x-axis twice. Bottom line is this. F of x has to equal to 0, which means x-intercepts, for at least 1x in the interval a to b. I can do a quick other example. Let's say I have f of a over here and f of b over here. Notice that in order to connect these two giant blue dots, I have to cross the x-axis at least once. Maybe twice, maybe 3 times, but at least once. That's what the intermediate value theorem says, that your graph has to equal to a y value of 0 for at least one time between a and b. So how is this applied to a problem? Let's look at this example down here. Show that this function has at least one 0 in the interval 0 to 2. So what we're going to do is we're going to evaluate f of 0. and we're going to evaluate f of 2. F of 0 is 1, which is positive. F of 2. Now, let's see what is f of 2 going to be. All right, so we have 8 minus 12, which is negative 4. Negative 4 minus 24 is negative 28. Plus 1 is negative 27. Oh, this is negative. And so, here's the conclusion. Since f of 0 and f of 2 have opposite signs, that was the requirement of the for the intermediate value theorem. F of x must equal 0 at least once in the interval 0 to 2. All right. To finish this lesson out, I want you guys to do the calculator review problem on your own and have it done before class starts. Have a good day, everyone.